Hi students, welcome to preliminary chemistry and the energy topic. This is video number 8, and in this one we're going to have a little bit of a look at some of the comparisons between alkanes and alkenes and some of the important factors associated with their storage and use. So the first thing we'll look at is a comparison of melting and boiling points. The first thing that needs to be said is small molecules have lower melting and boiling points than large molecules. We would expect that something like methane, which is a very low melting, very small molecule, would be a lower melting point and hence gas at room temperature than something like octane, which is a liquid. Melting point and boiling point increase as the chain length increases, and this is a result of dispersion forces as the molecular weight increases. So dispersion forces, if we have chains of hydrocarbons, what's holding these chains together are dispersion forces. So the longer the chains, the more dispersion forces exist between the two molecules, and the more energy is needed to separate them. The other thing that's important is that alkanes, generally speaking, have a lower melting and boiling point than the corresponding alkane, because the double bond just reduces the number of dispersion forces around each molecule. Effectively, there's two less hydrogens, so there's going to be a slight drop in the amount of dispersion forces between them. And when we talk about corresponding, we say, for example, this would be ethane. This would be ethene. So we would expect this one to have the slightly lower melting and boiling point than this one, than the ethane, just because there's a couple of less hydrogens and therefore there's slightly less dispersion forces between the adjacent molecules. Remember, if we want things to change state, we have to move the molecules apart from one another, or at least allow them to slide past one another. Volatility is another term that's important to have a look at. It applies to alkanes as well as alkenes, and it describes substances which vaporize at room temperature to produce a higher vapor concentration above the solid or the liquid phase. So if we have a container and this container has a liquid inside of it, then some of the molecules are vaporizing. So they're becoming a gas, and they're becoming a gas that's actually going to sit, blue color here, on the just on or near the surface of the liquid. Of course, if it all escapes, then it doesn't create very much vapor pressure. The higher concentration of gases in this region is known as the equilibrium vapor pressure, and it just means the pressure that the gas is applying at this interface between the gas and the liquid. Now, some hydrocarbons vaporize very readily at standard laboratory conditions. In fact, you know, when you go and fill your car at the petrol station, you can actually see some of the vapors escaping as you pump petrol into your car. And this is, sadly, you're paying for that petrol that's disappearing. But it means that we can see that there's a ready transfer of molecules from the liquid phase into the gas phase, even at those lower temperatures. Again, as a general rule, the lower the molecular weight, the greater the rate of evaporation and the higher the volatility. And again, this is a result of weak dispersion forces. So if there are weaker dispersion forces between the molecules, then if we have two molecules that are close together, again, being held together by dispersion forces, then it's easier to break something like this than something like this that has more dispersion forces, and therefore this one is going to be more likely to separate and create individual molecules which are going to sit above that other state, the liquid or the solid. As a result of this, boiling point is a good indicator of volatility because we know that low boiling points means a lower amount of energy required to pull those molecules apart from one another. And so volatility increases with increasing temperature. On warmer days, you will have more petrol being lost. Early morning's a good time to fill up your tank because it's the air's not as warm. And so therefore at a lower temperature, there'll be less volatility and there will be less loss of molecules. Related to the concept of volatility is this idea of flashpoint. And flashpoint is the minimum temperature at which the vapor pressure of a hydrocarbon is sufficient to combust in air. So again, if we have a look at our container and it has our hydrocarbon sitting in here, so maybe this is octane. And then we have a layer of gas molecules sitting above it. Well, if those molecules can be encouraged to ignite or to combust, then we have the flash point. Okay, that's when we've got the flash point. Combustible fuel air mixtures can be dangerous because any spark or flame can ignite them straight away. And the higher the boiling point of a hydrocarbon, the higher its flash point. And that kind of probably makes sense to you. Solid waxes have higher boiling points and flash points than liquid hydrocarbons. And it's these strong dispersion forces that makes them less volatile, and that lowers the vapor pressure, which can also raise the flash point. Effectively, the two things that are happening is the force of attraction between molecules, and that's a consequence of the dispersion forces, and that's related to volatility. And of course, flash point is about the chemical change, so it's about combustion. What happens when the fuel combines with oxygen and you get combustion occurring. So liquids like octane have weaker dispersion forces between molecules, therefore they're more volatile, they have lower flash points. So we want low volatility and high flash points. If we have high volatility and low flash points, then we've got a spark that can just set the whole thing alight. So that, I guess, means we've got some significant implications for storage and use. So just to finish off here, there's a lot of points here, and all of these are sensible. If you've ever been involved in transferring petrol from a shed into a lawnmower, for example, or filling up your cars, you'll know that there's a couple of important things that we need to remember when we're dealing with hydrocarbons. We need to make sure that any gases are stored in carefully sealed airtight containers that need to be checked regularly for things like barbecues. We need to make sure that liquids are stored in clearly labeled metal containers with narrow openings. So think again of your lawn mower fuel. They need to be in these metal containers, narrow openings, and a really tight lid. Any fuel should be stored in cool, well-ventilated spaces. We don't want the volatile mixtures to build up. Any liquid transfer should be done outside. So if everything's in the shed, you need to move it outside, outside to fill. So you should actually be filling your lawnmower, for example, outside, not inside the shed. Flammable liquids have specific labels. These are HAZCAM labels, and they should be displayed always to warn of any dangers associated with any particular fuels. And it's also a good idea to have a fire extinguisher around just in case any of these things do start to combust. There's a lot in this video, and I guess we will continue to have more of a look at the hydrocarbons as we go through, but that should give you a good little overview before we go through and have a look at a few more of these things during the lessons. So thanks for watching.